So I'll use this video to introduce to you the concept of differentiation. So let's start with the motivation of learning differentiation. When we were learning EMF graphs, let's say we are given this curve and there's a point P on the curve. If we desire to get the gradient of the tangent of the curve at this point P, then the EMF way of doing it will be to draw a tangent at P and get the gradient of the tangent via y1 minus y2 over xy minus x2 by choosing, say, another point on the curve, on the tangent. But there are few issues with this approach to get the gradient of the tangent um, of a point on the curve. So the first problem is that um, the tangent gradient is dependent on how it's drawn. Meaning, everyone will most likely draw a different tangent, and hence your second point, this point here, will likely be different. So our gradient will all likely be different, even though we are finding the gradient of the tangent at the same point, which doesn't make sense because the gradient of a tangent at a point should be a fixed number. That is a correct answer in that sense. Okay, so second method, or a second problem, which is extension of the first problem, is that a slight deviation in the angle of the tangent may lead to very different gradient values depending on the scale used in drawing the graph. Okay, the last one is um, although you only draw a tangent once normally when solving a question, but what if we are supposed to find the gradient of 10 different tangents? Okay, it can't be that we will draw 10 different tangents on the same graph. Okay, so in this sense, this method is laborious and inefficient. What we desire now is for method to get an expression, hopefully, for the gradient of the tangent at any point. Okay, so our objective is to get an expression that gives us the tangent, the gradient of the curve at any point on the curve. So we start with looking at this great tangent. So let's say this great tangent has a correct answer, correct gradient that we call it M. Okay, there is a correct answer M. Okay, what can we do to find the value of M? So firstly, without drawing a tangent. Okay, so firstly, let's see that if I use another point, okay, Q here on the curve, okay, use another point Q, and we join P to Q, we join P to Q, then we can calculate the gradient of PQ, okay, given any 2 points P and Q on the curve. So let's say the equation of the curve is y equals to fx. Then what will happen is, let's say point P has a certain x and y value, x1, y1, and point Q have a certain x and y value called x2, y2, then the gradient, okay, let's not use 1 and 2, okay, let's use P and Q. So we have xp, yp, and xq, yq, okay, to represent the 2 points. So the gradient will be yq minus yp over xq minus xp. But to make my analysis easier, I'm going to remove xq. Instead, we are going to use another formula for gradient that you learned in set 1, which is change in y over change in x. Alright, so let me remove this objective here. Okay, and I'm going to expand from that part. So if my gradient of PQ is my change in y over change in x, so if I draw it out, your gradient triangle, this is my change in y, sorry, this is my change in x, and this is my change in y. Okay, so the change in y and change in x can actually be calculated in terms of f. So the point Q has xq comma yq, but since my change in x is change in x, I can rewrite this instead as xp plus change in x, comma f of xp plus change in x. Okay, because I'm actually setting xq to be xp plus change in x. Okay, because xq, the x coordinate of point Q is simply the x coordinate of point P plus this change in x that we want. Okay, so if we write it into our change in y over change in x, or yq minus yp over xq minus xp, then what we have is f of xq minus f of xp over xq minus xp, which is f of xp plus delta x minus f of xp over delta x. Okay, this may look very intimidating now, so I'm going to give you an example so that you can see how do we use this. Okay, so let's say we have the curve y equals x squared, and my point is at the point, so let me call this y equals x squared, and I'm at the point 1 comma 1. So you can choose point Q to be anywhere else. So this is my point P. So let's say we choose point Q to be 1.1 comma something lah. Okay, so which means in this case my delta x will be 0.1. Okay, because 1.1 is 1 plus 0.1. So my Q's y coordinate will naturally be 1.1 squared, since my equation is y equals x squared. So my gradient of PQ will then be 1.1 squared minus 1.1 over 1.1 minus 1. Sorry, 1.1 minus 1.1 square minus 1 square, which is 1. Okay, so you will get 1.21 minus 1 over 0.1, which is 2.1. So my gradient PQ here, the gradient of PQ is 2.1, which will not be the same as the gradient of the tangent passing through Q. Okay, let me redraw that. Okay, so let's say this is the red line is the actual gradient. So this gradient M here will be the actual gradient of the curve at point P. But right now, I have the gradient joining P and Q, which is 2.1. So I hope you can see that clearly the gradient 2.1 cannot represent the value of M, which is the red line's actual gradient. So then how do we make this process better? If we shift Q towards P, downwards here, that means now I move Q here. Then my gradient triangle gets smaller and the gradient of PQ will now be much closer to the actual gradient M. Okay, so I repeat this part here. This working here will approach the actual or the correct gradient of the curve as delta x gets smaller. Okay, so we are trying to approximate the gradient of the red tangent using these 2 points here, P and Q, which are both on the curve. And the approximation will only get better if point P and Q are very close. So we want the chord's gradient to be close to the gradient of the red tangent. If the point P is too far from point Q, like what I have illustrated here originally, then it's easy to see that the gradient of the chord will not approximate the actual gradient in purple here. Okay, so let's use another Q here. So if I now change Q to not 1.1, let's say we change Q to 1.01, which means that I'm using my delta x as 0.01, then we'll get 1.01 squared. Okay, so now my new gradient PQ, okay, will be 1.01 square minus 1 square over 1.01 minus 1. So what you should get when you evaluate this is you should get 2.01. And in fact, the choice of delta x being 0.01 is arbitrary. You can actually choose it to be even smaller if you want. Okay, if we choose now delta x to be 0.001, my M of PQ, okay, you may want to go and check, repeat the calculation and check that you understand what I have been trying to say up to thus far. You will get 2.0001. Okay, so you can see that as your x gets smaller, the decimal point of 1 will actually get larger. So it's not difficult to guess that as your delta x decreases towards 0, my MPQ should become the value of 2.000 blah 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 than 1. With so many zeros in between, effectively it is actually just 2. So the gradient of PQ, or rather the gradient of the tangent at point P at 1, 1 should be just 2. So this is a very important concept that will allow you to find or approximate most of the curves given to you. Okay, hence we have this second table here. Given any new curve and you want to find a gradient, you can always try to find a pattern by getting arbitrary x values. So let's say the usual set that I would choose is -2, -1, 0, 1, and 2. And write down your y values there. Okay, so for the previous example, my y value is x squared. So your y values you fill it up like your table of values. The only difference is now you have additional row called gradient and you will repeat the MPQ calculation that we did just now, which is for every single x value, you choose a delta x that is small enough, find the y2 minus y1 over x2 minus x1. Okay, so let's say try not to choose a delta x that is like 0.1. Okay, that is not good enough. So normally I will recommend you to choose, let's say, delta x to be 0.001. Okay, so I will show you one time for x squared, let's say for -2. So your next x value would then be -1.999, because from -2 I add 0.001, comma -1.999 squared. Okay, so your gradient calculation will then be your y2 minus your y1, which is 4, over your x2, which is -1.999, minus your x1, which is your original -2. So key this in your calculator, and you should get about 4, or rather -4, for -3.999. You will round this to the nearest whole number, which is -4. Okay, so okay, let's not write it there. Let's write it in the working. So -3.999, which is approximately -4. Then you put -4 here. Okay, so I repeat, let's say we do it for 1. So your second point will be 1.001, comma 1.001 squared. So your gradient is 1.001 squared minus 1 over 1.001 minus 1. So you will get 2.001, which is approximately 2. So you put 2 here. Okay. So you can actually use this same method to find now the gradient of the curve at any point. Okay, it need not be a whole number. If let's say now we want to find the gradient of the curve x y equals x squared at, let's say, 100. Okay, never mind. Let's choose a nicer number. Let's say 23.4, comma 23.4 squared. Then how do you get the gradient here? So since you set delta x to be 0.001, we'll just find 23.401 square and 23.401, sorry, 23.401 as the x value, and the y value is 23.401 squared. Okay, hence your gradient at x equals to 23.4 will be given by y value minus y value. Maybe should be 23.4 over x value minus x value. Okay, and this will give you a good approximation, typically for you to see what is the value of the gradient. Okay, so now I'm going to return back to the discussion of the values here. You will, if you repeat for -1, 0, 0, 2, 4, you will get the following numbers. Okay, so the purpose of constructing this table is that most of the time your gradient values will have a pattern with either your x values or your y values. Okay, I think for this example, it's not hard to see that the pattern, so we are always trying to find a pattern for y equals to x squared, is that the gradient is 2 times the x value, which means the gradient is 2x. Okay, so if you don't believe, you can try for, let's say, x equals to 3 now. You can check for 3 comma 3 squared versus 3 comma 3.001 comma 3.001 square, whether 3.001 square minus 3 square over 3.001 minus 3, which is the approximated gradient, is it equals to our pattern here 2 times x. My chosen x value is 3, so is it equals to 2 times 3? Okay, you should get a number similar to it. Okay, so this method will allow you to find and establish the pattern of the gradients in terms of x and y. So I will show you one more time, then we'll be the end of this example. So let's say now we move on to x cubed. It will be tempting to check whether, so let's say pattern for y equals x cubed. Since the pattern for x squared is gradient is 2x, 2 times x. So we want to check whether the gradient for x cubed is it 3 times x value, which is 3x. Okay, so first thing, repeat the working here, fill up your x and y value. So same thing, I'm choosing -2, -1, 0, 1, 2. So you get -8, -1, 0, 1, 8. Okay, and go and fill up the gradient row. So if I want to show you again, so let's say I choose -1, 1, then we are comparing -1, 1 versus -0.999, comma -0.999 cube. So we'll get -0.999 cube minus -1 cube over -0.999 minus -1. So keying this into our calculator, you will get 2.997001, which is approximately 3. But our guess is supposed to be 3 times x. Then it's supposed to be -3 because the x value is -1. So our conjunction is wrong. So go and fill up the other 4 values. Okay, then we will review what will be the pattern for y equals to x cubed.